So I have a couple of examples and then another couple, a few from the practice exams. So the first one involves I will try to divide it between Gauss's law and problems involving like integration, like Coulomb's law. So let's consider a disk. This is a disk with a hole in the middle. So this is a hole. There's nothing in the middle of the disk. Okay. So the disk has a hole in the middle. The inner radius here is, let's call it, we can call it A and B. Let's call it R1 and R2. R1 and R2. So again, in the middle it's empty, and in here there is a charge density. What kind of charge density will it be? Is it going to be rho, sigma, or lambda?
Sigma.
Sigma. So there's a charge density in the middle, and it is sigma. And let's say sigma is some number. Let's say, or maybe not a number. A over R. So A is a constant. And that's C. So in the middle it's empty, and this is sigma. And we would like to now say electric field at distance R from the z-axis. Okay? I'm sorry, distance z along the z-axis. What is the electric field along the z-axis? So find the electric field at distance z along and the z-axis is the axis of the z-axis is this one. Okay. Any suggestions on how to do that? Yes, please.
Well, we can use two different things. We can split that into two different disks, like a disk of rho, both of rho, but the inner one's negative.
Okay. And then?
And then just calculate the electric fields for those, and then add them together because it's equivalent.
The only issue, we don't know what the electric field for a non-uniformly charged disk is. If we did, then that would be a possibility.
So, we do the thing with getting the disk from infinite rings.
Okay, that's what I want to hear.
Yeah.
So let's do rings. So we can think of this as made of many rings. The first ring begins at r equal to 1, and the last ring begins at r equal to 2, r2. So here are the rings. Radius little r, and they look like this. And so there is charge here, right? There is charge over here. And the thickness here is dr. Dr is the thickness. So we could, let's first ask, what's the charge sitting on that ring? dq will equal to sigma times dA, right? Where A is the area of the ring. So let me change this to letter B. Okay. just not to get confused. This is just a constant. Let me call it B instead of A. B. That's better. Sigma is BA. Well, sigma is B over R. What's dA? What's the area of that ring? Radius is R. Thickness is dr. You should know this. 2 pi r times the thickness, dr. So the circumference is 2 pi r by dr. So it will be the area, dA is 2 pi r by dr. So we can cancel the r. And so dq is going to be 2 pi b dr. That's dq. Now, we know the equation for a ring. The electric field due to a ring. The electric field due to a ring, that's called a dE. You remember this. I'm going to write it, it's Z times Q, but we're going to call Q as dQ, divided by 4 pi epsilon naught times Z squared plus R squared. I'm doing this from memory. Correct me if it's wrong. I think it's correct. This is the electric field for a ring. The distance Z above the ring. Sounds correct. Okay. So that's what we're going to do. So it's one of those things you should remember or write in your cheat sheet. Otherwise, you have to derive it during the exam. Okay. So then, to find the electric field, E, I'm going to write it in brown here. E equal to the integral. Let's put it all together. Put up the integral. Z times dq. So we got Z times dq, which is 2 pi b times dr over 4 pi epsilon. And then 1 over Z squared plus R squared. Oh, should be a little off. And so E would be 2 pi E Z over 4 pi epsilon naught integral from integral and then dr over Z squared plus R squared to the 3 halves. And you have to figure out what are the limits of integration.
So R1 to R2.
From R1 to R2. The middle is a hole. It's empty. From R1. Then you can integrate this. We did this integral before, and you can do a trig substitution, or you can look it up. Yeah. Yeah, it would be an easy U substitution if we had an R here, but we don't. So, the physics is done, the rest is math. You look up this integral and yes.
No, thought I remembered it.
Oh, you thought, yeah. Let's see, would be the tangent squared. I'm sorry, tangent squared plus 1, the tangent, so you get secant squared on top, becomes secant cubed, so it'd be cosine, integrate, you get sine, and then it'll be something. I forget what the exact answer was, but my aim is not to do the integral, at least not today. In an exam, if you need such an integral, I will provide it for you.
What direction would it be? What direction would it be?
If it's positive, it's going to be in the positive z direction.
Would it be in the r hat direction?
No, just the z direction. Yeah, it's going to be along the z direction. Remember when we had the dq here, we produce a field that way and another one this way. Only the z survives. Yes.
I think it's for r equals z tangent theta, the integral ends up being sine theta over z cubed.
Something like that. Yeah. And then sine, you have to convert it back to r.
Yeah.
Yeah. So you do it on your own for this one. So my point is, how do we deal with this? And we dealt with it. The rest of it is evaluating this integral. And I want to spend more time on physics today.
How did you know the electric field wasn't like constant? Like you had to integrate d by e. Like how did you? Would the problem tell us that's like not a uniform charge?
I told you, yeah, it is a non-uniform.
Oh,
Depends on what it was.
I missed that one.
Yeah. So we were told.
Gotcha.
Here's a simple question. What if sigma is b times r instead of b divided by r? What would change? Just go here and put b times r instead of b divided by r. That's the only thing that would change. Did you have a question? By the way, I'm recording it. Hopefully it doesn't fail. The recording will go through, and then I will upload it again. I will upload it to. I'll give you the link for the YouTube. So the next one, let's do a flux problem. We have been doing flux problems. Let's do one. Suppose. That's the first example. Example 2. And then I have a couple from the practice tests. And then, unless you have ones you want to ask me. So here is a flux problem. Suppose we have a box, let's say this room, and there is a charge. And so here is. And for simplicity, I'm going to make the box into just a cube. It would be a cubical box. Here is the, let's say, the z-axis. Here is the y-axis. Here is the x-axis. Sounds good. Suppose charge enclosed is let's say let's do 20 epsilon naught. The charge enclosed is 20 epsilon naught. Of course, charge is in coulombs. So this number 20 must have units of coulombs divided by the units of epsilon naught. So the number 20 here has some units. Anyways, but the charge, this number 20 times epsilon naught would come up to be in coulombs, so that the charge is in the right meters. The reason it shows it to be 20 epsilon naught, can anyone guess why it shows the charge equal there?
So look right stand side of Gauss's law equals just 20.
Exactly. When you put Gauss's law, charge enclosed over epsilon naught, when you divide by epsilon naught, the epsilon goes away. It's just for, so we don't need a calculator. That's all. And let's say the box is 1 by 1 by 1. Okay. So this is position 1 on the x-axis. This would be position 1 on the y-axis. And this would be position 1 on the z-axis. 1 meaning 1 meter. Everything is SI units. Everything is in. Sounds good. So the charge is sitting somewhere in the middle. I have no idea where. So, and let's say the electric field is given by x times I hat plus 3 times j hat plus some constant a times k hat. That's the electric field. This is the electric field. It's 3-dimensional. And the question is, find A. Calculate A. We would like to calculate A. So Gauss's law. I think it's clear we should use Gauss's law. If you have charge enclosed, and you're given the electric field, and there is a relationship between the electric field and the charge enclosed. The charge enclosed, we know E dot dA, closed loop, closed surface integral. Q over epsilon naught. And so again, Q enclosed is 20 epsilon naught divided by epsilon naught. That will equal to just 20 in the appropriate units. In that case, it's going to be newtons per coulomb meter squared. Newton meter squared. Okay. So far, so good. So how are we going to find this letter P? Well, we need to do the integral, E dot dA. It's an easy integral. Well, not bad. The closed surface is this kind of surface, right? It has a front, a back, a top, a bottom, a right, a left. Let's start with E dot dA. So this closed surface integral will involve 6 integrals. 6 integrals. E dot dA at the top, E dot dA bottom, E dot dA front, back, left and right. So it's right. This closed box consists of 6 faces. All of these 6 sides. So we need to do E dot dA for each. So let's do the top and bottom. Let's start with top and bottom. So E dot dA top. In what direction is the area at the top? Yes.
Positive k hat 1.
Exactly. The area at the top points in the k hat direction, right? Remember this ceiling here points upward. So the area at the top points in the k hat direction. So we're right. Yes. This is the electric field. This is the electric field. And the area points in the k hat direction. So if you do the dot product, what do you get? Let me do it for one of them more explicitly, and then I will be less explicit afterwards. So x I have plus 3j plus a k hat dot the area, but the area points in the k hat direction, right? It's in k hat direction. So what's the dot product of I hat dot k hat?
0.
Here, affirm 0, right? j hat of k hat?
Zero.
0. K hat of k hat?
1.
1. So this ends up being a times dA, little a times dA. So it ends up being like this. And this is just a times a. And what's the area?
1.
It's 1. Yeah, the area is just 1. So we just get a. So from the top, we just get a. Yeah. Is anyone? How did the other question go back?
How did the big A go away?
The integral of dA. This little a is a constant, right? So the integral of dA is just a, and the a is the area, so it's 1 by 1, which is just 1 square meter. So capital A is just 1. That's not a half. Okay. Let's do the bottom. This one is going to be just as easy. In what direction is dA now? What? Down, right? Yeah. So minus k hat direction. So this would be exactly the same, except for here you have minus k hat. So it will end up being
Minus A.
minus a. Okay, so I skipped some steps, right? And it ends up being minus a. Let's do left and right. E dot dA. Left. E dot dA left. In what direction is the area on the left? It's this space, right? So it points left, which is negative j hat, minus j hat direction. So what changes here, you would have dA but j hat, negative j hat. So the dot product, what will it come out? The I hat becomes is 0, right? When you dot it with j hat. J hat dot j hat is not 0. So it becomes what? Who can tell me? Huh? Yes.
Just becomes 3.
3. Huh?
Hmm?
It becomes what? 3. What?
Oh.
Or just 3? That becomes just
Well,
negative 3.
3A, but 3 integral of 3 dA, just get it, and then 3 goes outside. The integral of dA is integral of dA is a, which is 1, so 3.
Just 3, right? But don't remember the don't forget the minus sign because it's to the left. So it's
Oh,
going to be
okay.
minus 3.
So,
So it will end up being minus 3, right? End up being minus 3. How about E dot dA from the right? What changes? Huh? So to the right, it will be positive I hat, so it's going to be positive 3. I just made up this problem, so hopefully it comes out correct. Okay. My goal was to review what flux is, how to work with flux. Okay. Now, we did top, right and left, and now we need to do front and back, yes.
How come we didn't use E and cosine of theta, that formula, instead?
EA cosine theta, but what's cosine theta? It's either,
Would it be 0? Because, I mean, they're all parallel to each other, right?
Yes, so that's what it does. So if it's parallel, it would just be cosine of 0, which is.
Yeah.
Yeah.
So can't we just do E and equal to 20?
The,
Or take the magnitude of the electric field and.
so you're saying why not do this? EA times cosine?
Yeah.
You would, if you only, if you were given cosine theta of, that the vector dA makes with E. If you're not given this, you're given just two general vectors. So here, you have to actually do the dot product. It's actually easier this way. And then, what should we do next? The front, right? E dot dA front. So we do- this one is gonna be not as simple. So, E dot dA. In the front, in what direction is the area? Towards us, which is positive x direction, right? So it's dA times I hat. So that's, if you have here dA times I hat, so you have x dot, x I hat dot dA I hat, what's the dot product?
It's X.
Just x, yeah. It's going to be x. Yes? Are we okay with that? It's gonna be this. X times d. dA. Please let me know if this is not making sense. Okay, slow down. It is making sense.
I agree.
Yeah. Well, I said I can slow down if it's not making sense.
Oh,
So you read down the question.
Can you go over one more time how you asked?
So let's write down the electric field explicitly and dA explicitly. The electric field, of course, is this. It's given to us. So it's x I plus a plus a. Okay. Dot product with, you said dA is in the I hat direction, right? So the dot product is going to be x I hat dot dA I hat. What does it do? What's the dot product? I hat dot I hat. Did you say that? It isn't it? Yes. What is j hat dot I hat? Yes.
0.
0. K hat dot I hat?
0.
0. So these contribute nothing. And then I hat that I hat is 1, so you end up with just x times dA. Yeah.
Correct me if I'm wrong, but when you're done with all of the sides, you just kind of add all those integrals together, right?
And we should get 20 if I set up the problem, if I chose the numbers correctly. And let's hope so. Yeah. I should have maybe added a variable here or something to make sure that it's, so if they don't end up, if it doesn't end up to do that, it means well, let's do it. That's always a risk when you make up a problem on the spot. So we get this. X times dA. So now that's it. So now we cannot just pull out the x because x is not constant. X here, x times dA. This is the front end, correct?
I was,
Yeah, that's the front end, yeah. Actually, x is constant. How much is x in the front end?
1.
Just 1, yeah. The front end. Do you agree that x is 1 in the front end? So you get, and a is 1. should have chosen a 20x. So maybe this should have been 20 times x, yes.
I also don't think you're gonna be able to find A.
Let's see what we get. Anyways, is this clear? At least the process. Process is clear. So can I change it to 20a? Or maybe at the end, if it fails, I will change the number here to make it work. So let's do the back. What changes from this? What's the only change?
Negative x I had.
This will be in the negative I hat direction, right? Yes.
Also, x equals 0.
And x at the back end is how much? Yeah, x at this face here is 0, right? So we will get this. We will get x times negative dA, right? But x itself is 0. X is 0. So this is just 0. That's 0. Okay. So, so before I proceed, can I change this? I'm going to make a change so that the problem will work out. I should have chosen here at 20 x to 20x, so that here we have 20. Here should be 20, so that the number here is, it ends up being 20. And here it's 20, but x is 0 anyway, so that's 0. So, what's the total flux? What can we say about E dot dA? Closed surface integral. Well, let's say to get the total flux, you need to add all the fluxes. The flux through the top, bottom, left, right, and front and back. So you get A, right? Plus negative A, so that's 0. Minus 3 plus 3, that's another 0. And then plus 20 plus 0, so you get 20. Get 20, right? Newton's meters to Coulomb. And 20 is equal to 20, so it works out. So what should A be? Yes,
Anything?
it could be anything. So A doesn't matter. So little a is, doesn't matter. Could be 1, it could be 7, it could be something. Sorry, I should have worked through this problem before giving it to you. Yeah.
Will there ever be something on an exam where the answer is just like anything?
I will work out the numbers better if I ever have that. Yeah. Yes.
Can you explain again why x I had on the back is 0?
Oh, what is x here? It's 1, right? This is
Yeah.
the x-axis. Where is the back face? Back face is here. It's on the YZ plane. At the YZ plane, x is 0.
Okay. But you wouldn't make, like negative j hat on the left wouldn't be 0, though.
But x itself is 0.
Okay.
Yeah, so let's say here is the origin of this corner. Right? Let's say this is the x-axis, and this is the face, right? So what's x at this point?
0.
And at this point?
1.
It's actually still 0.
Oh.
Because x, this is the x-axis.
Oh.
That's the x-axis. So this is x equal to 0, over there is x equal to 1. Yeah.
That makes sense.
Yeah, good.